Good morning. In this video, we are going to discuss proposition 4 from book 2. So this proposition declares that if we are given a finite straight line AB and a random point P on this straight line that cuts AB into two different segments, A and B, and it declares the square on AB, which will be L square, will be equal to the sum of the two squares of these two segments, two squares, and twice the rectangle contained by these two segments. Okay, let's try to prove it. So first of all, please recall proposition 46 from book 1. We are allowed to construct a square on a given straight line. So let us construct this square ABCD on the given straight line AB, okay? ABCD, great. And then let us use postulate 1 to construct a straight line BD by joining them. Good. And please recall proposition 31 from book 1. We are able to construct a straight line through a given point that is parallel to a straight line. So let us construct ABCDE, PE through point P that is parallel to BC and AD. And in the next point, let's assume they are meeting with each other. The PE meeting the diameter at the point of F. And let's use proposition 31 again to construct a straight line through point F and parallel to AB. Let's assume these 2 points are G and H. Okay? So currently we know that AGFP, GDEF, and FECH and PFHB, they are 4 parallelograms, right? Because the opposite sides of them are parallel to each other respectively. So for convenience, let's temporarily mark them as R1, R2, and S1 and S2, okay? So we know they are parallelograms, okay? Great. And now please think about proposition 29 from book 1. So if two straight lines is cut by another straight line, then the exterior angle will be equal to the opposite interior angle. So please have a look at these two straight lines. AD is parallel to PE, correct? And DB is straight line falling upon them. So we have this angle will be equal to this exterior angle, interior opposite angle, which means let's mark it as angle 1 and angle 2. So angle 1 will be equal to angle 2, correct? And please think about ABCD. This is a square, and because of the definition of a square, it is equilateral, right? Definition 22 from book 1. So we know that AD will be equal to AB, correct? They are equal. It is square. And if we recall proposition 5 from book 1, in a triangle, if it is isosceles, two sides are equal, then the related two angles are also equal. Okay, so pay attention to this triangle ADB. These two sides are equal, so related angles are equal. Let's mark it as angle 3. So we have angle 1 equal to angle 3, great. And if we combine them together and apply combination 1, combination 1 will tell us that angle 1 is equal to angle 3, correct? 1 equals 3. And let us use proposition 6 from book 1. So in this triangle, if two angles are equal, then the two related sides are equal, correct? Oh, my bad. This should be angle 2 equals to angle 3, correct? So they are equal. So pay attention to this small triangle, BFP. So these two sides are equal, sorry, these two angles are equal means PF will be equal to PB, correct? And we know this is a parallelogram, so if we apply proposition 34, we know that the opposite sides are equal, which means PB equals to FH and PF equals to BH, correct? And if we combine them together, we can conclude that this parallelogram is equilateral, okay? So it is equilateral of parallelogram PFHB, correct? Okay, so now we know it is parallelogram. Equilateral, equal, okay? And in the next step, please also recall proposition 29 again. So the two interior angles, the sum of them will be equal to two right angles in two parallel lines. Okay, so still using AB is parallel to GH. We know that angle BPF plus angle PFH will be equal to two right angles, correct? And we know that BC is parallel to PE, so we can conclude that angle BCP. So these two angles, the sum of them are two right angles. FPB plus angle PBH will be equal to two right angles. Okay, so just keep these two equalities there, and recall proposition 22 again. The square is right angled. So ABCD is a square, which means this angle must be a right angle. So we know that angle PBH is a right angle. Okay. So now if we combine these three equalities together, we know that PBH is right angle, and the sum of them, let's say this is a right angle, and the sum of PBH and FPB is two right angles, so which means this must be another right angle, and BPF plus PFH is also two right angles, and one of them is a right angle, so which means another is also a right angle, correct? And if we apply proposition 34 again, the opposite angles of a parallelogram are equal. So this is a right angle. The opposite angle, this is the fourth right angle. So which means it is right angled of parallelogram PFHB, correct? And now let's combine this conclusion and this conclusion together. So, and still recall definition 22 from book 1. If a parallelogram is both right angled and equilateral, then it is a square. So we know that PBFH is a square. Okay. So similarly, we just give the specific steps. We can prove that GDEF is another square. So let's just write a conclusion here. GDEF is a square. Great. So let's just keep these two conclusions here and keep an eye on AGFP. Okay. So we know from definition 22, this is a square ABCD. So this angle must be a right angle, and we've already know that AGFP is a parallelogram. So say R1. So recall the definition of a rectangle. If a parallelogram contains two straight lines that contains a right angle, then it is a rectangle. So AGFP is a rectangle. Similarly, we can prove this is another rectangle. ACHF is another rectangle. Let's just skip steps. So keeps these four conclusions in mind and what we can derive. Okay, so let me check. I'm sorry. So we have this is a square, so PF S2 is square, so S2 this is square, so S2 will be equal to B square, correct? And this is another square, so we know S1 will be equal to A square, correct? And the rectangle R1 will be equal to AB, correct? And similarly R2 will be equal to AB. Correct? We have these four equalities, and let's say the whole square ABCD is S. So let's mark square ABCD, let's say it is equal to S. And what S is? S equals to R1 plus R2 plus S1 plus S2, correct? And if you still remember proposition 43 from book 1, we know that two complements about the diameter of a parallelogram will be equal, okay? So keep in mind, this is a diameter and this square is absolutely a parallelogram. R1, R2, R2, they are two complements about the diameter of the point P, so they are equal. So we know that R1 equals to R2. So from this, combine these two equalities, we can conclude that S will be equal to twice of the R1 plus S1 plus S2. And let us just plug in these four equalities into this equality. So we know that S equals to L square, correct? It is square. Equals to 2R1. What is R1? AB. Let's plug it in. 2AB plus S1. Also plug it in here. A square. S2. Plug S2 here. Plus B square. Okay. So here we have proved our proposition, and that is the end of proof. And to be more, I think to be more concise, this is so-called the square of the sum formula. So if we write it into algebra expression, it will be simplified as this. A plus B square will be A square plus twice of AB plus B square. This is a very typical square of the sum formula of algebra, which is exactly equivalent to our proposition, but Euclid had proved this proposition in geometric methods rather than the algebra expression. Okay, and that's the end of the video. In the next one, we are going to discuss proposition 5 from book 2. Thanks for watching. Have a good day.